From an airplane, this area looks pretty much the same. Some sand dunes, trees, and bushes. But if you walked through this area, you'd find several different ecosystems. An ecosystem is a community of living and non-living things interacting within their environment. These young students explore the forest ecosystem where raccoon, deer, and woodland birds make their homes. The vegetation varies from the lush fern to the tall and sturdy birch. Another ecosystem is the nearby marsh. Of course, some plants and animals may live in more than one ecosystem. Would the blue heron of the marsh also nest in the field? What similarities could Nathan and David discover between the field and the dunes? These hills were formed by the glaciers of the Great Ice Age, which left vast deposits of sand along the lakeshore. The strong winds off the lake keep the sand hills constantly changing. When you think of a pretty flower, do you only think of a garden? Here flowers grow and blossom as they do in the springtime fields. What can we learn by studying plants of a certain ecosystem? Let's investigate one of these ecosystems with Nathan and David and see what we can learn about the plant life in it. To investigate, we need to carefully observe. When we observe, we use our 5 senses: sight, hearing, taste, touch, and smell. This special ecosystem is called a bog. David and Nathan observe, using their sense of sight, the different forms of vegetation, like these lily pads. Their sense of smell indicates dampness and decay. And their sense of touch? What can they observe with that? The ground, for example. The solid ground moves as if it were on springs. This is because the combination of peat moss and extremely wet soil make floating mats that move with your every step. It's like bouncing on a bed. The bog was formed during the Ice Age thousands of years ago when the glacier left broken masses of ice and huge potholes. As the ice melted, vegetation took over the potholes, which had little or no drainage. To observe the bog further, Nathan and David have brought various field guides for help and a notebook to record their data. In their exploring, the boys discover the sundew. This bright red plant can capture and hold an insect by a sticky substance that it produces. Because the sundew absorbs the insect as food, it's called a carnivorous or insectivorous plant. The same is true of the pitcher plant. Here, a cricket is caught in the pitcher plant. The slick, bristly leaves of the plant prevent the insect's escape. The pitcher plant secretes an enzyme that helps it dissolve or eat the insect. David and Nathan are intrigued by the pitcher plant and want to know more about it. They've observed it's a pitcher plant by comparing what they see with the descriptions in their field guide. The guide gives a picture, description, and basic information about the plant. But what else can we observe about it that our book doesn't tell us? How many plants of this species will we find in the different ecosystems? Where do they thrive? Let's do some scientific investigation. We'll make observations about the pitcher plant, and we'll record the data we've observed. We'll start by counting the pitcher plants in the bog area. This information is called quantitative. When we count or measure, we use numbers. Numbers give us an exact quantity. Other information such as, is the soil wet or dry, is called qualitative. This information uses our senses, what we think or feel. Here are two statements. There were several pitcher plants near the pond. There were 15 pitcher plants within 1 meter of the pond. Which statement is quantitative? There were 15 pitcher plants within 1 meter of the pond. This statement is quantitative. The bog is large, and it would be difficult to count all the pitcher plants in it, so let's take a sampling. We'll make a transect line. A transect line is a narrow line or strip that goes through the area to be studied. The path from the park gate to the pond runs in a straight line, so we'll make this our transect line. Counting pitcher plants along this transect line will give us a sample number of pitcher plants in the bog. The boys will pace the distance from the gate and count pitcher plants within 1 square meter at every 10 paces. The same person should always do the pacing. Nathan's pace has been measured at about 1 meter. The length of the transect line was 120 meters. The boys are careful not to harm the pitcher plants. Nathan will do all the counting. David will do all the recording. Distance from the gate and number of pitcher plants, quantitative data. Soil conditions and sunlight, qualitative data. Once the data is gathered, the quantitative data can be displayed using a graph. The boys will use a line graph. A line graph is a good method of visually showing the relationship between two variables. The distance from the gate is one variable, and the number of pitcher plants is the other variable. The boys will title the graph Number of pitcher plants along a transect line in the bog. First, we draw a horizontal axis and a vertical axis. Along our horizontal, or x-axis, we label the first variable distance, or number of paces along a transect line. On our vertical, or y-axis, is the second variable, the number of pitcher plants. Referring to our data, we will plot the graph. At 10 paces from the gate, there were 10 pitcher plants counted. At 20 paces, 15 pitcher plants. At 80 paces, 40 plants were counted. We can see from David and Nathan's line graph that the number of pitcher plants increased as the boys went closer to the center of the bog. Except for one spot at 50 paces. Referring back to the data, the qualitative data shows that at 50 paces, the soil was damp, but not wet. Could this have made a difference in the number of pitcher plants thriving in this spot? The water in the bog is sharply acidic. This means it's like vinegar. How does this affect the soil? Do pitcher plants grow only in acidic soil? Let's make a map of the area and use the quadrat system to compare pitcher plants in different soil areas near the bog. The quadrat method uses plots of a standard size, randomly located within the study area. Nathan paces off quadrats 30 meters by 30 meters. Remember, each of his paces was measured at 1 meter. The scale for our map is 1 millimeter is equal to 1 meter. He ties a marker at the corners of the quadrat to mark the boundaries. David records all the data. Our map will show the general area of the quadrats in relation to our transect line. The 5 quadrats are located in the forest, in the bog south of the pond, in the field, the marsh, and the blueberry patch. The boys will count all the pitcher plants in each quadrat. This is their quantitative data. They will also note the moisture of the soil. This is their qualitative data. Taking a soil sample from each quadrat, they'll do a pH test. A pH test is the measure of the acid in the soil. The lower the pH number, the higher the acid content. This sample has a pH of 4, which is more acidic than average. Here's the completed data. Once all the data is gathered, it can be displayed using a bar graph. The title of this graph is Number of Pitcher Plants Found in 5 Quadrats. A bar graph is another way to show a series of variables. On the x-axis, we label the 5 quadrats. On the y-axis, the number of pitcher plants. The graph shows that the forest and the field had no pitcher plants. The pH of the forest soil was 5, and the pH of the field was 8. Both had dry soil conditions. The quantitative information of the forest quadrat and the marsh quadrat are quite different. The forest shows no plants, and the marsh displays 25 pitcher plants. But both quadrats have the same pH of 5. The soil of the forest is fairly dry. The soil of the marsh is highly saturated. What can we infer? In other words, what conclusions can we draw from our data? When we make conclusions about what we have observed, we make inferences. Can we infer that pitcher plants need acidic soil and saturated conditions to thrive? Or can we infer that there are a number of conditions required to have an ecosystem that's good for pitcher plants? What else could we learn about this varied and interesting area? We've learned that by carefully observing, collecting, and recording data, making maps and graphs, the world of scientific investigation gives us a better understanding of the ecosystems we see every day. David and Nathan learn to have fun with science while exploring the plant and animal life that is all around us.
Why did this cow moo? Why does this chicken peck the ground? It's all animal behavior, the different ways in which animals act and react to different things. Many factors affect the way animals behave: the weather, the seasons, survival, and also things we don't understand yet. Nathan wants to conduct an experiment on animal behavior. Where does he begin? He begins by observing animals in their environment. If we were to change a factor in their environment, how would they behave? You could conduct an experiment that focused on the animal's response to this change. Nathan is going to begin by making observations and collecting some data at Becky's farm. He hopes this could become an interesting project for a science fair. Before Nathan can conduct an experiment, he will follow these steps. He will state the problem, formulate a hypothesis, and then design the experiment. After conducting the experiment, he will organize his data using a data table and graphs, and then state his findings. What about the cows? Could Nathan observe their behavior in the field or their eating habits? They're a little large, and their environment covers a lot of ground. Maybe something smaller would be better. Becky suggests taking a census count of a small area with smaller animals. A census is a count of the population of a given area. For example, how many insects are in a square meter of ground? Along with census taking, they'll use these skills. They'll map quadrats, graph their data, and classify. This is all part of conducting an experiment. They map a small area by pacing. A pace is 2 natural strides. Becky records the measurements. The area measures 11 by 20 paces. They can accurately measure Nathan's pace by averaging the number of his paces in 5 meters. His pace is measured at 1 meter, so the area is 11 by 20 meters. The next step is to pick small areas to study. These must be picked at random. How could they do this? Good idea, Becky. These spots must be marked. They'll make quadrats. A quadrat is a standard-sized plot randomly located within the study area. A stake is planted near the marker. They measure off 1 meter and plant another stake. Nathan and Becky continue marking the quadrat until they have a square, measuring 1 meter on each side. They mark the boundary with string. They then take their census count. The census count will be quantitative data using numbers. Numbers give us an exact quantity. Becky will count all living animals in the quadrat. Nathan records as Becky counts. They do several quadrats for comparison. The second quadrat includes this log. They'll check under the log. You should check every inch of the quadrat. You'll never know what you might find. Here they found a slug on the underside of the log, and a cricket. Becky finds a number of sow bugs, more than any other animal. Nathan records the census. Here's his quadrat data sheet. They observed 10 sow bugs. There weren't any sow bugs in the other quadrats. They wonder why. The other quadrats were in open grass. Could that have an effect on the sow bug population? Well, Becky and Nathan have done a lot of observing, and they've taken lots of data. But what about designing an experiment? Nathan still isn't sure of what to do. At home, Nathan tries classifying the sow bugs. He observes they have a hard shell, a segmented body, antenna, and 10 legs. Using the same method scientists use to classify, a dichotomous key with couplets, Nathan learns that insects have only 6 legs and not 10. The sow bugs aren't insects or bugs. They're isopods, and they are closely related to lobsters. Nathan made a map of the quadrat area and titled it. The scale of the map is 2 squares equal 1 pace. From his map, we can see where the quadrats are located. The only quadrat that contained sow bugs was quadrat 2. Sow bugs were found only under the log and not in the open grass. What can Nathan infer from his data and observations? Could this be an idea for an experiment? In conducting an investigation, the first step is to state a problem. Nathan's problem could be stated as, do sow bugs prefer darkness? His problem should guide him to a hypothesis. A hypothesis is the relationship between variables. Based on Nathan's problem, the hypothesis could be stated as, the less light in an area, the greater the number of sow bugs. Now to design the experiment. Nathan has a few ideas, and with Becky's help, they should be able to conduct a controlled experiment. They'll be using sow bugs and cellophane gels, and also intervals of time. The cellophane gels will be used to control the amount of light falling on the sow bugs. First, a rectangular pan is divided into 3 equal sections. This is the experimental pan. It's covered with strips of gel. Clear, gray, and double gray gel. The gels are the manipulated variable, the variable you introduce into the experiment. A second pan is divided into 3 equal sections. This will be the control. The standard all results are compared to. The clear gel alone will cover the control pan. Nathan and Becky have collected 60 sow bugs for the experiment, 30 sow bugs for each pan. The responding variable is the sow bug's reaction to the different amounts of light. But how will they measure behavior? By the number of sow bugs in each section. This is their operational definition for behavior. At 10-minute intervals, Becky will quickly count the number of sow bugs in each section. That's how they'll measure behavior or preference for light. They will do this for 6 intervals. The variables held constant are the type of pan, the location of the pans, and the number of sow bugs. Nathan will record the data. He will use a data table. A data table organizes information efficiently. After 10 minutes, Becky counts the sow bugs in the experimental pan and in the control pan. At the end of an hour, 6 10-minute intervals, the sow bugs in the control pan were randomly distributed. This was not true for the sow bugs in the experimental pan. The data table for the experimental pan looked like this. They have completed the experiment, but they aren't finished yet. Becky and Nathan will now go over their organized data and display it using graphs. The next day, Becky visits Nathan. Each has made a graph of the experiment. Nathan's displayed the data using a bar graph. The graph is titled Sow Bug's Response to Varying Amounts of Light. The manipulated variable, the gels, is the x-axis. The responding variable, the number of sow bugs, is the y-axis. His responding variable is based on the total number of sow bugs present in each section after 1 hour. Nathan has found another way to display his graphs. He can use his computer. You use the same variables and the same x-axis and y-axis that you would use when drawing a graph. The graph shows that the clear gel, allowing the most light, had the smallest number of sow bugs. The double gray, which allowed the least amount of light, had the most sow bugs after an hour. Becky made a line graph. The title of the graph is Sow Bug's Response to Varying Amounts of Light Over a Period of Time. Her key shows the colors representing each gel. Her graph is different from Nathan's. It shows 3 variables. Her x-axis is the 6 time intervals shown in minutes. Her y-axis is the number of sow bugs. The colored lines represent the number of sow bugs under each gel over a period of time. Her graph shows a decline in the number of sow bugs moving to the clear gel. The gray remained almost constant. And a definite increase in the number of sow bugs that moved to the darkest gel, the double gray. Whichever way you choose to display your data, The next step is to state the relationship observed between the variables. What did Nathan and Becky observe between the manipulated variable, the amount of light, and the responding variable, the number of sow bugs? They observed that the less light falling on a section, the more sow bugs were found there. And their findings? Did the observed relationship support their hypothesis? The less light in an area, the greater the number of sow bugs. Yes, the results of the experiment supported their hypothesis. It's important to repeat your experiment or have it repeated by others. This helps verify your results. To conduct an experiment, you need to state a problem, formulate a hypothesis, and then design the experiment with two parts, an experimental and a control. After conducting the experiment, you organize your data and then state your findings. Do the results support your hypothesis? Designing a scientific investigation and conducting an experiment requires many of the skills you already know, such as graphing and formulating hypotheses, plus some new skills like stating a problem and stating your findings. Put all these skills together and you can learn a lot about animal behavior or any of the many fields of science.